Heat exchanger sample problem number 4. So for problem number 4, we are given with a counterflow, then double pipe heat exchanger, which is used to heat water from 20 degrees Celsius to 80 degrees Celsius at a rate of 1.2 kilogram per second. The heating is to be accomplished by a hot geothermal water available at 160 degrees Celsius at a mass flow rate of 2 kg per second. The inner tube is thin-walled and has a diameter of 1.5 cm. If the overall heat transfer coefficient of the heat exchanger is 640 watts per meter square degree Celsius, so what is the length of the heat exchanger to achieve the desired heating? So these are our assumptions. So steady operating condition exists. The heat exchanger is well insulated so that the heat loss to the surrounding is negligible, and thus heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. Changes in kinetic and potential energies are negligible and there is no fouling. Fluid properties are also constant, wherein for water, we will evaluate it at the mean of 20 and 80. So that's why we have 50 degrees Celsius. So the Cp at 50 degrees Celsius from the table is 4.181 joules per kilogram degrees Celsius. And for the geothermal fluid, since we don't have the value for the living water, so that's why we have 160 degrees Celsius. So we will evaluate at the inlet. So the Cp is 4.34 kilojoules per kilogram degree Celsius. So the next step is to establish the working equations for the unknown. So we are going to determine the length, and we can get the length from the surface area, because we know that for this tube here, since this is a thin tube, so the area will just be pi dl. So from that, we can get the value of the length. And then we also know that area is related to Q by this relationship. So Q is UA delta T, where area is pi dl. So we substitute pi dl and then rearrange to solve for Q, to solve for L. So the equation is Q dot over U pi d delta T ln. So we don't have yet the value of Q. We already have U, that is 640. The diameter is 1.5. So the unknowns are Q, heat transfer, and LMTD. So for the first unknown, which is the rate of heat transfer, so our Q can be solved using either from the geothermal water or from the cold water, depending on the availability of the temperatures. But since for the cold water, the inlet and outlet temperatures of the water is given and the mass flow rate is also given, we can solve for the Q from this cold water, such that Q is mCp delta T. So mass flow rate is 1.2, Cp of water is 4.181, delta T is 80 minus 20. That's why Q is 301.032 kilowatts. For the other unknown, which is LMTD, so this is our working equation. So as you can see, we need to solve for the leaving temperature of the hot geothermal water for us to use this equation. Before that, let's calculate delta T1. So for LMTD, one of the requirements is delta T1. Delta T1 is TH in minus T cold out. So the hotter of the two fluid is your hot geothermal water, which is 160. So the T cold out, so the colder part is your cold water leaving at 80 degrees Celsius. That's why we have 80 degrees Celsius. So we need to solve first for the T hat out. We already had T hat in, but we need to solve T hat out for us to get the value of delta T2, because delta T2 is T hat out minus T cold in. So for T hat out, so we know that the heat exchange is between the cold water and the hot geothermal water. So the Q that is coming from the geothermal hot water is also being absorbed by the cold water. So they are equal. So the Q for the cold water is just equals to MCP for the geothermal water. So where the mass flow rate of the geothermal hot water is 2 kilograms per second, CP for geothermal hot water is 4.34, and then our delta T is T in 160 minus T hat out equals to our Q. So from that we can solve for the value of T hat out and eventually substitute this to our equation for delta T2, so that delta T2 is 105.319 degrees Celsius. So we can now solve for LMTD since we already have all the values of the temperature. So our LMTD is 92.08 degrees Celsius. So substituting LMTD and Q to our working equation established in step number 3, we can solve for the length as 108.4 meter. So there is a need to make the length 108.4 meter to achieve this desired heating from 20 to 80 degrees Celsius.